Till, and this is a short talk I will give at the Dutch Day on Combinatorial Optimization 2022 at CWI Amsterdam. My talk is about R Matroid realizability is ER complete. This joint work with Arnaud de Mesmay, who you can see here, and Eunjung Kim, who I visited in May 2022. So let me start to define the two terms in this in the title of the talk, so that you should know those. First is, what is a matroid? So think about a set of vectors that you have, and then for each subset of these vectors, you can say, oh, those are dependent on each other. That, for instance, if the zero vector is in there, or if two of them sum up to the third one, or they are independent. So let's say three vectors are independent if they span a three-dimensional space. Now, matroids are an abstraction of that. That means they satisfy certain three axioms that these independents, the system of vectors, would satisfy. But they may be an arbitrary set of elements, and you assume you have this oracle which tells you who's independent or not. They're just satisfying some axioms, and they're not necessarily coming from some vectors. So it's a generalization, and there are also other things that can be seen as a generalization that matroids generalize. So, but one way of looking at them is seeing them as a generalization of these independences of vectors. Now, the realization problem is, I give you the matroid, find me vectors which have the same independence. So that's for each subset, they're independent if and only if the set of vectors, the subset of vectors, is independent. And that's a realization question. And if we talk about our matroid realizability, we ask about vectors, vector spaces, the real vector spaces, which is in some sense maybe the most common one that you can think of. So now you know what a matroid is, and you want to know what R matroid realizability is. So second question, what is ER complete? I'm assuming not all of you have heard what ER completeness. The simplest way I like to think about it is, think about NP completeness. You have a witness, which is some combinatorial information, and then you verify that the witness gives you the correct solution on a word RAM. Now, for ER completeness, it's defined as problems for which you have a real valued witness, let's say points in the plane, some vectors, whatever, and you can verify that this witness is correct on a real RAM, which can do basic operations with real numbers instead of just integers. And all of those problems which can be recognized in that way, they are forming a class of ER problems, and then the most difficult ones of them are called ER complete. Okay, so now you know the definition. Let me give you two pieces of the proof. The first piece is, if you think about some vectors here, you can flip their sign, and it doesn't change whether they're dependent or independent with some other vectors, because they are scalar invariant. And because they're scalar invariant, what happens, you can make sure that they're all intersecting this plane. Say if you have vectors in R3, this plane z equals 1. And then you get suddenly, instead of talking about vectors being dependent or independent in this plane, you talk about triples being collinear or not collinear. So that's the correspondence when you go from 3 dimensions now to 2 dimensions. So we will work with matroids for which we know can be realized in R3, or we ask if they can be realized in R3, and then we can reduce this problem by actually looking if a set of points can be realized in the plane, where for some points we say these must be collinear and they must be collinear. Using now this translation into the plane, we can encode addition and multiplication using that we are capable of forcing certain lines to be parallel. This is because we can use projective geometry, where we have also intersections at the line of infinity. So those two lines here would also meet at infinity, and those two would also meet at infinity. Those lines with the same dash sum are parallel. And that's basically the core idea of the proof. These gadgets here, they're called Van-Stout constructions, and I think they're known for roughly at least 100 years. But apparently they have not been exploited in the context of our Matroid realizability. And with this, I'll thank you for your attention and goodbye.